Okay, today is the last day of this chapter. It's the last new stuff, and it's on symmetry. This one's a little trickier than some of the stuff we did before. Tomorrow, we get to pull it all together. I'll have a review day, and I will be pretty thorough in talking through what we've learned. So then the test is going to be on Friday. I'm aware it's a shortened day, but the good part of that is you go into the weekend, and the only thing you're going to have to do is a top 20, one of those 20-minute practice your basics kind of things. So it'll be a piece of cake for homework for the weekend. Okay, so the test is shortened. Also, we shortened up the test. We took out 4 problems off of it because it is a shorter time period. So it'll work fine. Yes, ma'am. Let me think. 9 problems. All right. So this mirror here is a reminder that we have symmetry on our face. If you look in the mirror and you've got an eye on both sides, your nose is kind of right in the middle. So if you draw a line right down the middle, you got some nose on both sides. But have you ever seen pictures of people where they replace the one side of their face with the other side of their face and they give them exactly perfect symmetry? It's actually kind of scary. Yeah, it's really creepy. It does not look like, whoa, it's like, what's wrong with this person? So we actually don't want perfect symmetry in a face, or we think they look freaky. Okay, so it's okay if like one eye is slightly different than the other. We're talking slight, like of course you have 2 eyes, but one is going to be maybe slightly different shape than the other. Maybe the eyelid's slightly different shape. Eyebrows slightly different on one side compared to the other. That's part of what makes us unique and what makes us human. But we generally have symmetry running down the middle, so that's y-axis symmetry. All right. Do we have any kind of x-axis symmetry going on? Not at all. Draw a line right through the middle of us, and the top and the bottom don't look the same at all. Okay, so, yeah, yes, if you had a head and shoulders on the other end of your body, yes, you'd look very unusual. Okay, so we have y-axis symmetry, but not x-axis symmetry, and there's a third kind of symmetry I want to talk about. Oh, quick plug for the lab. When's it due? Friday. Don't put it off until Thursday night. Get some done tonight. Get it over with, because really on Thursday night you should be studying for the test. Okay? All right, anyway. 3 kinds of symmetry. What would that have? What kind of symmetry? I know it's off a little bit, but generally y-axis symmetry. Okay, good. There's this kind. What's that? X-axis symmetry. By the way, you know this one is a parabola, right? And it's y equals x squared. Do you know what that one is? It's x equals y squared. I know some of you are thinking, but isn't there a square root graph in there somewhere? Yeah, this is the square root graph. And do you get, it's got a reflection of the square root graph right there? Does that make sense to you? And actually, I can show you why. It's kind of cool. You take this and you solve it for y. But don't make the classic mistake. Here's the classic mistake. People think, oh, so I'm going to solve this equation that's got a squared in it, that I should just square root both sides and I get x equals 4. No. And don't say it's just plus and minus. It's not. Because when you square root both sides, the square root of 16 is 4, but the square root of x squared is absolute value of x. That's a big deal. You're all grown up now. You can't have simple things like, oh, it's just plus and minus. I don't really know why, but it is. Square root of x squared is the absolute value of x because what you put in there could be positive or negative and come out to the same thing. That's because of the squared aspect of it. Putting in a negative or positive, either way, you get the same thing. All right, so the moral of the story is this comes out to x equals 4 and x equals negative 4 because of the square root thing. Take this right here, and I would like you to solve it for y. X equals y squared. Solve it for y. And you'll see why there's 2 parts to this thing. Okay, if I'm going to solve for y, what's the first step? square root, square root, square root. Okay? Square root of x, it's okay to leave it as the square root of x. The square root of y squared, you're going to be tempted to say it's just y, but I just tried to pound into your head that it was actually what? So the value of y, good. So why is that important? Because if you just said it was y, you'd have y equals x squared, and this, you would be saying, was exactly the same as the red graph. Do you get how it's not exactly the same as the red graph? Okay. The reason it needs to be absolute value of y is now I can split it into two things. Exactly what it is without the absolute values, y equals square root of x, and the opposite of that. You write the exact same thing and then slap a negative on it. And do you recognize this? It's the same graph except with a negative in front of it. And do you get that's the same graph except flipped? Remember the whole flipping thing? Okay, so then you get a separate part of the graph that goes like that. One thing, it's not a what? A function. Because it doesn't pass the what? Vertical line test. Okay, good. So this guy isn't a function. It's not like it's an illegal thing. It's a thing. It's just not a function. Okay. So now back to what were we doing here? We were talking about symmetries. So we don't require our things to be functions in the first place to have symmetry. This has symmetry. It's symmetry across this line, which is symmetry across the x-axis. The old-fashioned parabola has symmetry across the y-axis. Already saw that one. It's like this. Okay. But what about symmetry across a point? Have you ever heard of point symmetry? All right. It's symmetry across the origin. It's called origin symmetry. This one, I think you'll recognize this graph. Remember that guy? X cubed, very good. Okay. I kind of made it straight in the middle there. It should be more curvy, but there we go. X cubed graph has got some symmetry that you may never have investigated before. That point there, if you draw a line straight through the origin and out the other side, there's another point on the graph that's right there. This dot right here, if you draw a straight line through it, through the origin, see how it hits the other one? I'm off a smidge, but that's called origin symmetry, the special kind of symmetry. So I'll give you another example of that. Let's say, I'll make it much wider this time. Does it have x-axis symmetry? Does it have y-axis symmetry? Does it feel like it still has some kind of symmetry? And what's that symmetry called? Point symmetry, and the specific point in this case? Origin symmetry. All right, cool. And if you took a spot here and you went straight through there and out the other side, there would be a corresponding spot there. All right, now let's dig into that a little bit deeper. The one that I gave you that had perfect points, it's a little narrower and harder to see, but I'm going to slap it back up here. It had 2, 8, and it had -2, -8. Do you get that if I take this point 1, 1, the other point that's like it is actually -1, -1? And 2, 8 turns into what? -2, -8. So would you say in general that x, y turns into what? -x, -y. Awesome. That's origin symmetry. If -x and -y go with x and y, then you've got origin symmetry. Let me show you how this can get more complicated. No picture. Do you remember the simplest of all of these, which was x squared plus y squared is equal to 4, and it was a what shape? Ah, it's on my true 20. It's not the top 20, it's the true 20. The circle. Circles are things that can be on the ACT test. So when you see this thing, think circle. It's a circle with a radius of what? 2. Awesome. So if I change it to this, it'd be a circle with a radius of 20. All right. Then, if I wanted to move my circle, I would put like this and go like, oh, now my circle's moved 2 to the right. You know what I'm talking about? But this one's a circle that has not been moved. It has been stretched. Very good. So it's a circle that's been stretched in both directions, and all of a sudden it's not looking very circly anymore. It might be more like that, an oval of some sort. Okay? So the question would be, does this thing have point symmetry? Or sorry, does it have origin symmetry? Does it have x-axis symmetry? Or does it have y-axis symmetry? Special deliveries for you. Yep. This is a good thing. I know what they are. Okay. So here's how you can tell. First, I strongly recommend you take this and make it your premier example of how to do this. Because there's one problem like this. I'm trying to decrease your stress. Normally I don't tell you how many problems of what kind are on the test. I will tell you in this case. There's only one question on like this on the whole test. But there is one question like this on the test. Okay, so if you get everything else, there's 9 questions tomorrow. Sometimes there's 13 questions. In this case, there's a 9-question test. Not tomorrow, but sorry, on Friday. And there's only one of them like this. So if right now you're thinking, this is really hard compared to that other stuff, yeah, it is. And it is an honors class. So, but there's only one question like this. You would understand 8 out of the 9 questions if you didn't understand this, but you understood the other stuff. Okay? So most of the questions are pretty easy. This is the tough one. All right, so what kind of symmetries does this have would be the question. So make a really good, nice, long, good set of notes on this right here. So here is the first little set you need. You need what is x comma y. That's if I put in x and y into this equation. I know that seems dumb. I already have an x and a y. But if I stuck an x right there and a y right there, of course, I would get the original equation back. That is the original equation. So I'm going to write it. 5x squared plus 3y squared is equal to 25. If I put in x and y as normal, I will get the original equation. What's that rule we just did a second ago called origin symmetry? What's the rule for that again? Negative x and negative y. Take a guess what I'm going to want you to do then. Stick in negative x and negative y into your equation. So I'm going to take the same exact equation that I had, except instead of the x, I'm going to put an empty spot. 5 something squared plus 3 something squared equals 25. And instead of x, I'm going to put in what? Negative x. Negative x. Don't pick a number, because you'd have to pick a number that exactly worked in this function. And that's a pain in the butt to like try to find an exact pair that works in this function. Okay? So we're just going to use negative x and negative y. And now we simplify it. And if it comes out the same as the original, you have proven that those get along, and therefore it's got origin symmetry. All right, so let's simplify this. What is 5 times negative x squared with the parentheses in that spot? And that's why I said to put parentheses there. Because actually, if you didn't have the parentheses there, it would come out different. Because if there wasn't the parentheses around that, the squaring wouldn't hit the negative. It's an important fine point that a lot of kids don't know. I'm going to step aside for just a second and show you that. A lot of kids don't get that this is different than this. In fact, as a math teacher, I was kind of sloppy with that in middle school, I'll admit. And it's a big deal at the high school. Happens all the time. One of these is positive 25. I bet you can tell me. Which one? The one with the parentheses. But a lot of you, I bet, would have said that was positive 25, and it's not. Okay, and you can try it on your calculator and you find it's negative 25. Unless you put parentheses around it, and then it will be positive 25. So it matters that there's parentheses, right? Okay, so that's why those parentheses matter in my example. Some kids are going to leave off the parentheses right there. And then it also can start looking like 5 minus x squared, which is totally different than 5 times parentheses negative x squared. So put in those parentheses, please. Otherwise, I'm not going to be able to give you the credit because your work's not going to actually be right. All right, so if I have the parentheses there, then when I square it, I'm going to get 5x squared back again, plus 3y squared equals 25. We have proven that this and this come out the same, and therefore we've proven it has what kind of symmetry? Origin symmetry. All right, now all you need to know is the other rules, like this. So let's talk about this kind of symmetry again. What kind of symmetry does that have again? Y-axis symmetry. And if this is at 2, 5, then what's this spot over here going to be? And therefore, if this is x, y, what does y-axis symmetry need to have? Do you get how you can recreate that even if you forget which one's which? You can draw yourself a little picture of one that's even and recreate it. All right, so moral of the story, this shows y-axis symmetry. I am a big guy for like remembering shortcuts. I like things that help me remember dumb things. You know, like please excuse my dear Aunt Sally helps remember the order of operations and stuff. Well, that's the kind of symmetry. The one that doesn't have the negative, that's the kind of symmetry it is. See what I'm saying? So that's the y-axis symmetry test, is the y does not have the negative on it. Okay, so then I can just see one and go, okay, x comma negative y, it must be what kind of symmetry? X-axis symmetry. All right, so the one that doesn't have the negative on it, it's that kind of symmetry. All right, so this one's for y-axis symmetry. You got to prove negative x comma y. All right, so let's do one. Would you agree that this should have y-axis symmetry? X squared plus 16. Think about it. Parabola shifted up 16. Should it have y-axis symmetry? Yes, it should. So let's prove it. You're going to have f of x here. You're going to have what? Or sorry, no, not f of x. X comma y here, sorry. And you're going to have what for the other rule you're trying to prove? Negative x comma y. Prove it. You haven't caught on yet. You will soon. I sense you might be in a different place. To be able to do this, like write it out on your iPad or on paper, one or the other. Or unless you can actually draw, like write it out, which I think is theoretically possible. I want to be able to see that on your screen. Just like everybody else is doing right now. I'm going to pause for a second while I come and check a few. I got to give some guidance here because a lot of people weren't sure how to start. This is just if you stuck x and y into this function. You'd get the same thing. So you're basically just recopying the function right there. How many of you guys had that part right? Okay, good. Then, on the other side of your t-proof thingy-bob, we're going to stick in negative x into the same function. So I'm going to drop it right there. Do you remember me saying that I should put in empty parentheses where the x and y were? Were the parentheses important? Yes, they're a huge deal when it comes to a negative. Whether it's in or out of a parentheses totally changes it, so put in parentheses. Then, in this case, we're going to drop in a negative x where the x was. We're going to drop in a regular y where the y was. And then we solve it down. And we see if it's exactly the same as the other one. Y is just y. Negative x squared is x squared. And look at that, identical, thus proving what kind of symmetry? It's the one that doesn't have the negative on it, and therefore that has the negative on it, therefore it's y-axis symmetry. Yes? if I have that and that, they are the same, because no matter what you put into them, when you actually do it, you actually do the squaring and everything, they'll come out the same. Is that what you were saying? You were correct then. Good. Just making sure. Whenever somebody says always or never, I got to be really careful, because those are dangerous statements in math. So. All right. So we proved this thing had y-axis symmetry. Would you please prove for me that this thing does not have x-axis symmetry? All right, the setup is huge, and I got to make sure that you know how to set it up. So would you set it up, please? Show me what's on top of the chart here at minimum. Otherwise, you're lost, and you should ask the kid next to you. Good question. We already proved it has y-axis symmetry. Now I'm asking you to prove, I think we all know it doesn't have x-axis symmetry. You got to prove it. I'm going to pause for a second while you set that up. Okay, I think you guys are setting it up right, but let's check. Did you have x comma y? Can't write. Did you have x comma y here and negative x comma y there? True or false? That would be testing for y-axis symmetry, and we already tested that. That's false. It should be x comma negative y. Now we're testing for what kind of symmetry? X-axis symmetry. Okay, good. So now this one is a no-brainer. Why is it a no-brainer? It's the same thing. It's just going to be the original. Y equals x squared plus 16. What's really happening is you're sticking in an x and a y for the x and the y, and they come out the same. Then you have the same thing here, except what am I going to say to right? That I made a big deal about? Parentheses, yes. And what do I drop into said parentheses? Te. Yeah, nope, KF. Yes, you. I don't try to say the full names on the videos, so go ahead. All right, I'm putting in a negative. Oh, over here? Excellent. And then over here? Regular x, I agree. Now I should simplify this thing down. What do I mean by simplify it down? Solve it for y again. Try to make it look exactly like the other one, okay? So I'm going to simplify this, get it down to just by. I'm going to multiply everything by -1. That'll do it. And do you get that I have positive y equals negative x squared minus 16? Does that look like that? Therefore, no symmetry. Does not have that kind of symmetry. All right. Lastly, don't even do it, but if you were going to do it, how would you test for origin symmetry? Raise your hand if you can explain the difference. Yes, Miss H? Yes, a negative right there would do it. We plug in negative x and negative y and see if it simplifies down to the same thing as this. Cool. All right. You know your 3 kinds of symmetry now. I'd like to see if you got them all straight. I'd like you to set up a T-chart for testing something for x-axis symmetry, set up the T-chart for testing something for y-axis symmetry, and set up the T-chart for testing something for origin symmetry. Just the top of the chart. We're not actually going to use a real function here. It's kind of like the review portion. Sum it all up. Okay. For x-axis symmetry. Did you say x, y, and, well, it's kind of x, y, but what do I need to do to them? Negative on the x, negative on the y. X-axis symmetry, the negative is on the y. All right. And for here, x, y will go with x, y, but the negative is on the x. And last but not least, for the origin symmetry, x, y, we'll need to turn into negative x comma negative y. And as you're doing the rest of it, this is always the no-brainer part. You just copy the original function there. Duh. What's super important as you're doing this part? Parentheses. Put in your parentheses in the right places, and then simplify it down and see if they come out the same. Is there such a thing as something that would have all three kinds of symmetry? A circle. Very good. A circle would have all three kinds of symmetry. All right. Now, every circle? No. You take your circle and you shift it up here, and all of a sudden it only has one kind of symmetry. But if you put a circle right there, you could have a circle that would have all three kinds of symmetry. All right. Probably a reason that we use that a fair amount. It just has all this symmetry, and we kind of like how that looks. All right. So anyway, your homework for tonight, of course, is similar to that, but it reinforces a couple things that I haven't talked about in a while. What is the X-intercept of this? I know you right now could do the test to see if it has X-axis symmetry or Y-axis symmetry, or what's that third kind? Origin symmetry. Good. But would you know how to simply graph it? To graph it, all you really need to know is that this is a mutated circle. It had a radius of about what? 4, the square root of that, good. And it's been stretched a little bit, especially in which direction? The x direction. Okay, so would you agree that generally this thing might be kind of like this, or it might be kind of like that? It's some kind of a stretch in the x direction. All right. All right, so then here's the question. If I told you what the x and the y-intercepts were, would you be able to kind of know where it was? So then the last piece is, how do you find the x and the y-intercepts without the picture? Well, the x-intercept, I gave you a snappy saying the other day, the x-intercept is where y equals 0. So what do you think we do? We stick a 0 up in here. Do you get how that turns this into 0, and I just have to solve that little equation? Will it involve having an absolute value when you do it? Yeah, then you end up with 2 answers. Doesn't that make sense? That there should have 2 x-intercepts if it's going to be a circle? Probably. Because it's going to go like this, right? It's going to probably hit twice. So that makes sense. The x-intercepts, the y-intercepts. The y-intercept is where x equals 0. And if you can stick in x equals 0 into the equation, which is up here, I can put a 0 right here, and then I can solve it. Oh, that's an easy one, because this cancels. And can you solve that one in your head? And please don't say 4. 4 and negative 4. It's the absolute value of the y, which is going to lead you to 4 and negative 4. And does it make sense that you might have a 4 and a negative 4 for intercepts on a circle? Yeah. All right, cool. All right. So let's actually find the x and the y-intercepts for these guys. The second one's really easy. We just did it. But would you figure out the x-intercepts for me? Yeah, it's going to be an icky number, but that's okay. Just leave it as a square root. Find me the x-intercepts of that function. If you want a straight A on the test tomorrow, you'll have to be able to do that kind of a thing. Sorry. Keep saying tomorrow, I mean Friday. We have a review day tomorrow. So you don't have to be perfect yet. Yes? Because we won't have to do that? Not yet. It's on the top 20, so it's good to know eventually. But let's focus for right now on the tests. I don't have to know that for the test. You will have to know this for the test. So how do I get the y-intercept? That was x equals 0. That was the easy part. That was solve that. And they were y is equal to 4 and y is equal to negative 4. Those are my 2 y-intercepts. But the x-intercept is what you're working on right now. Mrs. T, or Miss T in the front row there. Y equals 0. Once I stick that in, what's the little equation that results? Which is just gone. Good, and then I'm going to divide by. Excellent. And then I'm going to have to take the square root. Please help me do that right. What's that side? Yes. All right, and you can say the square root of 16/5, or you can say, actually do the top, because the top works out. What is the square root of 16? 4. So you could say it's 4 over the square root of 5. That's okay. Or you could leave it as root 16/5. I'm okay with either one. And I'm going to need to split it into two answers. X equals the root of 16/5, and X equals the negative root of 16/5. All right, that's hardcore math. Those are your two X-intercepts. One of them's over here, one of them's over here. Do I know exactly where they are? I don't know. Do you know the square root of 16/5 off the top of your head? No. But if I made 16/5 into something nicer like 15/5, that would be about 3, right? So it's like the square root of 3, right? So therefore, a square root of 3 is like 1 point something, right? Okay, so it's pretty small compared to these others that were 4. So I could move this over and say it's pretty small. So can you generally see that which way a stretch happened here? It was kind of a circle, but now it got mushed down. Do you remember that when you put something like this on the outside, it's a vertical stretch? Does that ring a bell? Does this look like a circle that got stretched vertically? There we go. So it all makes sense. All right. Did you learn what x-axis symmetry was? Did you learn what y-axis symmetry was? Did you learn what origin symmetry was? Did you learn how to prove it by sticking like negative x into the equation? Then you learned what you were supposed to for today. Good. Okay. So your homework for tonight has 3 pages. My continuing commitment to make it reasonably sized. You may do the first 2 of the 3, and I believe that will be sufficient. So I'm going to go here and show you the homework starts after usually a blank page in the notes, okay? Then here we go, and it'll often have this little, I think I can say almost every time, it'll say exactly where we are, 1.2 day 2. It'll have that in the homework. That's a way of telling it's actually the homework. And now, this one is asking you to take that and tell what kinds of symmetry it has. I personally like that little T-chart thing that I was showing you. I think it's way easier than trying to do it in only this much space. So I strongly recommend you add a page and do it that way. And this, find your x-intercepts and your y-intercepts. You're going to do that by sticking in the y-intercept is where what? X equals 0. And the x-intercept is where what? Good. So this won't be hard to graph. That get the general idea of what it looks like. Do you get it's an x cubed function that's been shifted? Ooh, x. That's interesting. So generally, as it's been shifted, it's an x cubed function that's been shifted kind of up or down depending on what x is. All right, so you aren't going to know exactly what it looks like. That's okay. All I'd ask for is your x-intercept and your y-intercept. When it says sample points, that means pick a couple other points, like watch. Sample point is if I stick in x equals 2, for instance. Do you get how that's going to be pretty easy to do? Let's stick in a 2. I get 2 cubed is 8, minus 2 is 6. So that gives me 2, 6. That is a point that is on this graph. Because I pick any points I want. I can't do that for the x-intercept and the y-intercept because they are specific places. I can just pick a spot like, what if x equals 1? That gives me 1 cubed minus 1, which is 0. That leads me to 1, 0. Ooh, that actually turns into one of the intercepts because the x-intercept is where y is 0. That was actually one of the x-intercepts. I just found it by accident. But I pick any numbers I want for these sample points. Stick in x is 1, 2, pick simple stuff. Why torture yourself with sticking in x equals 5/3? All right, so this is about graphing it. And again, my recommendation to you is add a separate page to do your t-tests for these. So I'll start that by doing, oop, that wasn't supposed to happen. Alignment's off. To test y equals x to the 3rd minus x and see if it's got x-axis symmetry, I'm going to put x comma y, and x-axis symmetry would be x comma negative y. That's for x-axis symmetry. All right? So here's the beginning of your homework, how you're proving whether or not this has x-axis symmetry. The original's here, and the result one, when I stick in negative y, will go here. So here's my empty spot to the third minus empty spot, and I drop in x's stay the same. Y becomes negative y. Now I simplify it to solve it for y. Multiply everything by negative 1. Y equals negative x to the third plus x. Are these identical? No. So it does not have what kind of symmetry? It doesn't have x-axis symmetry. It might still have y-axis symmetry. It might still have origin symmetry. It's your job to figure out. And again, there's 3 pages like this. The first page is that one problem that I just started you on. The second page is this pink one. The third page is the green one, which you may happily skip, because I think you don't need that for extra practice. Now, you know, when I say you can skip it, does that mean you have to skip it? Of course not. But it also leaves, if you do skip them, it also leaves you something to do on the review for the test day. Remember me saying we're not going to give you a practice test? But if I skipped a few problems in the homework, that you can go back and actually do them now. It's a resource for you. You can actually go back and use those problems. Okay, that's all I got for you for today.